Welcome to part 3 of our binomial probability distributions video series. In this video, we're going to talk about additional properties of the binomial distribution, and we'll try to put it all together. Some major concepts are histograms for binomial distributions, computing the population mean and standard deviation for a binomial distribution, and computing the minimum number of trials needed to achieve a probability of success, P of R. First, let's look at graphing a binomial distribution. So to make a graph, what we're going to do is we'll place our R values or X values on the horizontal axis, and we'll place our probabilities here listed as P of R, but we might also have P of X instead on the vertical axis, and then construct the histogram. So the first thing I'm going to do for the example we see here for a distribution is I'm going to make a set of axes. We have a distribution in terms of X. So our horizontal axis will be not R values, but X values in this case. And our vertical axis will go P of X. For our horizontal axis, we have numbers 0, 1, 2, and 3. So I'm going to label those 0, 1, 2, 3. And I tried to make them equidistant. My probabilities go from 0.1 all the way up to 0.4. And we know we should always start our vertical axis at 0. So I'll go up by 0.1 until I get 0.3 all the way to 0.4. Now I can fill in my bars. The probability of 0 was 0.2. So I'll make a bar that goes to 0.2. The probability of 1 is 0.3. The probability of 2 was 0.4. And the probability of 3 is 0.1. Unless there's a gap in the data, meaning in this case, not really a gap, but a probability of 0, you should have no spaces between your bars. For our binomial distributions, we have special formulas for the mean, variance, and standard deviation. The mean, mu, is n times p, so your number of values times the probability of success. The variance, sigma squared, is n times p times q, where q is the probability of failure. Your standard deviation is the square root of npq, because remember, the standard deviation is the square root of the variance. Remember, just as we have in other sections, we can use the range rule of thumb to determine significantly low and significantly high values. So values that are at or above 2 standard deviations above the mean are significantly high. Significantly low values are at or below 2 standard deviations below the mean. Between that, we call it not significant. We can also determine significance using probabilities. And when we're using probabilities to determine significance, our magic number is 0.05. So a value x is called significantly high if the number of successes, x or more, that probability is less than or equal to 0.05. A number x is considered significantly low if a low number of successes if the probability of x or fewer is less than or equal to 0.05. Let's use what we've learned to complete an example about overtime rules in football. Between 1974 and 2017, there were 460 NFL football games decided in overtime. 252 of them were won by the team that won the overtime coin toss. Is the result of 252 wins in the 460 games equivalent to random chance? Or is 252 wins significantly high? We can answer that question by finding the probability of 252 wins or more in 460 games, assuming that wins and losses are equally likely. In this problem, we have n is equal to 460. The probability of success is going to be 0.5. How do we know that? It says here, equally likely. That means the probability of failure, Q, is also going to be 0.5. Our X value is 252 wins. Trying to find if 252 wins is significantly high. So we're trying to find the probability that x is greater than or equal to 252. Using my calculator reference chart, I know that for x is greater than or equal to problems, I use 1 minus binom CDF of my n value, which is 460, p, which is 0.5, and then I'm going to use my a minus 1, so 251. I'll use second vars and scroll down to binom CDF in my calculator when I'm finding that, and I'll get 0.022 as my approximate answer. Now, 0.022, let's see, we have to compare that number to 0.05. So 0.022 is less than 0.05. So in this case, we would say that 252 wins is significantly high. You can see since 0.022 is less than 0.05, it shows that it's unlikely that we get 252 or more wins by chance. If we effectively rule out chance, we're left with more reasonable explanation that the team winning the overtime coin toss has a better chance of winning the game. We can also calculate significantly high events using our range rule of thumb. Our previous example involved n equals 460 overtime wins in NFL football games. We get p is 0.5 and q is 0.5 by assuming that winning the overtime coin toss does not provide an advantage. So both teams have the same 0.5 chance of winning in overtime. So now, let's find our mean and standard deviation for the number of wins in a group of 460 games. And use that range rule of thumb to find the values separating the number of wins that are significantly low or significantly high. Is the result of 252 wins in 460 games significantly high? To find a mean for a binomial distribution, we take n times p, in this case 460 times 0.5, and we get the mean is 230 games. The standard deviation is the square root of npq, or the square root of 460 times 0.5 times 0.5. Standard deviation is 10.7 games. For random groups of 460 overtime games, the mean is 230 games. Standard deviation is 10.7 games. Notice the rounding to 1 decimal place, which is 1 further decimal place out than our original values. Use this mean and standard deviation to find out what 2 standard deviations above and below the mean are. That way we can find our range of not significant values and figure out what our significant values are as well. So when we do that, we're going to say that our mean at 230 and then 2 standard deviations above is 251.4 games, and 2 standard deviations below is 208.6 games. Anything that falls between these values is considered not significant. Anything outside of that range are significant values that are not likely to happen. See that 252 games falls outside of the usual range, so 252 is considered significantly high. Let's do one last example to tie everything together. A waiter at the downtown restaurant has learned from long experience that the probability that one lone diner will leave a tip is only 0.7. During one lunch hour, the waiter serves 6 people who are dining by themselves. Make a graph of the binomial distribution that shows the probabilities that 0, 1, 2, 3, 4, 5, or all 6 diners leave tips. What's the expected number of successes? And what is the standard deviation? Let's write down what we know. We know that there could be 6 diners, so n equals 6. And we know that the probability of a tip is 0.7. What we need to do is make a probability distribution with each of our x values and the probability of that x value occurring. So our x values go 0, 1, 2, 3, 4, 5, and 6. And to find the probability of them occurring, we're going to use binom PDF, and we use npx. So in our case, it's going to be 6, comma, 0.7, and then the x value for the particular row. Pause the video now and see if you can find all of the probabilities, and then we'll check our answers. Pause the video. You can see my chart where I have my numbers 0 through 6. And then I have the probabilities 0.001 for 0. Probability of 1 is 0.010. Probability of 2 is 0.060. Probability of 3 is 0.185. Probability of 4 is 0.324. Probability of 5 is 0.303. Probability of 6 is 0.118. And they add up. When I total this whole column, I get 1.001, which is okay. It's just off due to rounding. You can see all the way to the right, I have the steps that I put into my calculator. This is your required work for finding binomial probabilities. To make a graph of our binomial distribution, our x-axis will go from 0 to 6, and our y-axis will have our probabilities. So it should go to from 0 to at least about 0.4. Here you can see our probability histogram. You're also asked to find the expected number of successes. That's mu equals NP. So our N is 6 and our P is 0.7. 6 times 0.7 is 4.2. Now we need to find the standard deviation, sigma, which is the square root of NPQ, or the square root of 6 times 0.7 times, well, the complement of 0.7 would be 0.3. The standard deviation is 1.1. Knowing this information, I wonder, is one customer tipping significantly low, and is 6 customers tipping significantly high? To find this, I need to find out what 2 standard deviations below the mean and what 2 standard deviations above the mean is, because that will tell me what's significantly low and high using my range rule of thumb. So I can find my mu minus 2 sigma, which is 4.2 minus 2 times 1.1. That gives me 2. So if my mean is 4.2, 2 standard deviations below is at 2. I can find my mean plus 2 standard deviations. Well, that's going to be 4.2 plus 2 times 1.1. That gives me 6.4. 2 standard deviations above my mean is 6.4. I know any usual values will fall between 2 and 6.4. So I'm asked about one customer. One customer is right here. That is significantly low. So we can say yes, significantly low, because it's below my usual range. Whereas 6 falls within my shaded blue area. So it is not significantly high. We can also determine significantly high and significantly low using probabilities. Going to our probability table, to find the probability that one customer tipping is significantly low, we need to find the probability that x is less than or equal to 1. We can just add up our probabilities that x is 0 and our probability that x is 1. And what we come up with in that case is 0.001 plus 0.010. So we get 0.011. And we're going to compare that with 0.05. And the amount that we get is less than 0.05, which supports our answer of yes. See if the probability of 6 customers tipping is significantly high. We need to find out the probability of x being greater than or equal to 6. Well, in this case, it's just equals 6 because that's the highest number in our chart. And that is 0.118, which is greater than 0.05, which supports our answer of no.